Hello everyone, this is the next video of EE355 by Viterbi Bros, and today we're gonna talk about algorithms in general, or a quick tour about algorithms. So let's get started. So what's an algorithm? So algorithms is a set of rules or steps for a machine to solve a certain problems. So in real life, you can think algorithms just like a cooking recipe. So for example, over here, you can see we have like, before making a cake pop, the first step is kind of like getting all the ingredients that you need. The next one is like proceed the cake. So just like you buy your flours, milk, butter, eggs, you kind of mix them together, which is like one of the essential steps. And then you're gonna roll to make a like kind of like ball shape, a circle shape, and then you make your candy dressing, and then you stick like some plastic stick with your ball cake. After that, you dip it with your candy dressing. So the problem right here is how to make a cake pop, and this is an algorithm or instruction that help you to fix this problem or to make a cake. So an algorithm can be expressed in many ways. So I just show you an example of how to express an algorithm with your own language. By language, I mean like English. So let's go back here. You see, it's all English. If you're like a chef or you're like enthusiast person who love how to cook, then this is an easy algorithm that you can follow to make a cake. So that's why you can express like algorithm in your own language. And you can try with like German, Italian, Dutch, Spanish, any language that you prefer. Another way to express an algorithm using a flowchart, which is gonna be explained on the next slide. And the third one gonna be the pseudocode. So pseudo here means fake. So you can tell like, oh, pseudocode, it's just a fake code. The name is fake code, but the meaning is not really like fake code. So I'll also explain on the next slide as well. Lastly, it's gonna be programming language. So there are many programming language out there in the world. I'm gonna name some notable one. It's gonna be C++, which we're using in EE355, Python, C, C#, Java, JavaScript. You can name it, okay? And those last three are like widely used in real life, in the industry, by a professional, textbook, and workplace. So let's get started with flowchart. So in order to easily visualize flowchart, let's build a system called a grading system. So let's say you're a grader. When you grade a student, you have to certain threshold like, oh, if you grade greater than 90%, I'm gonna give you an A. You grade. But if it's failed, you have to go to the next condition. Okay, this person definitely not greater than 90. You're gonna check if he or she is greater than 80, and you give a B. But after that, if it's wrong again, if that person not greater than 80, then you're gonna check again another filter. You ask, oh, are you greater than 70? Then you give it a C. And after that, it's not working anymore, like the person grade is still not greater than 70, then you put to the next filter. You're gonna ask, oh, are you greater than 60%? If it's yes, give it D. And else, you just give an F, like that person failed the class. Okay? So let's see for flowchart. First, you have to enter in the grade, which is this purple box right here, entering the grade. And you're gonna ask, okay, are you above 90? And if it's yes, give you an A. And if it's a no, I'm gonna put another filter to ask, okay, are you above 80? And if it's yes, I give you a B. And if it's not, you pass your grade to another filter. Would ask, okay, are you above 70? If yes, you give a C. And keep going on until you pass to F. And why is it called a flowchart? So the reason why is, so flow actually stand for the arrow right here. And chart stand for the purple block, the orange block right here. So flow chart is kind of like the block that flow like this, as you can see. So that those two components make up the flow chart. And you can see when you enter in the gray, your gray gonna flow to here. If it's right, you go to A. If not, you flow to here. If not, you flow to here. If not, flow to here. In the end, if the gray of student didn't pass all this filter right here, he or she just flow to F, which means fail. Okay, so this is a flowchart of the grading system. So now let's express that flowchart or the algorithms in another way called pseudocode. So this is an example of the pseudocode. So first, let's dissect what is pseudocode. So as I mentioned before, pseudo means fake. Pseudocode means fake code. And why is that? Why is it fake code? So let's look at the chart on the right side. So you can see at the beginning, I'm asking, okay, if you're above 90%, I will give you an A. But else, if you're not greater than 90%, I will asking again, okay, I know you're not greater than 90%. Are you greater than 80%? If yes, I give you B. But what happens if it's not? You're gonna ask again, okay, now I know you're not above 80%. So are you above 70% as well? If yes, I give you a C. If not, you go down here again. Okay, now I know you're not greater than 70%. So now I ask you again, okay, are you above 60%? If yes, I give you a D. And else, you just fail my class. Okay? So that is just a simple pseudocode. And what's called pseudocode? So you can see the syntax where you have if, you have else if, you have else if, you had else if, you had else. And if you took programming class before, you can see if and else if actually borrowing from the real programming language like C++, Java, and Python as well. So all these language, they're using this kind of syntax like if and else if. But look at the inside. You are above 90. You are above 80. You're above 70. You're just English, plain English. See, English. So that's why pseudocode mean is a combination between programming and the real language that you're using. It just is acting like a code, but you cannot run it on any programming compiler because it's gonna spit out error because it's plain English. So that's why it's called pseudocode. The coder you try to fake it, but it's help everyone else who didn't know programming language still can understand it. Like us right now, let's assume you haven't taken any programming class before, but if you read this pseudocode right here, you can't understand it because you have English right here and have some sort of programming syntax over here. Okay, so pseudocode is a good way to start before implementing the real code, and it's very straightforward. So if you see right here, you have the if and else. You have the if and else. So if you're a Python programmer, if you read the pseudocode, you can translate to your Python code by dissecting like this. So you see if, you can translate to if, and you are above. You are here, mention the grade. So you can have a grade variable, like grade. Above 90%. So above, you can try it like this, and then you put 90. You see it? This is the pseudo, and in here you translate to Python code, So it's save your time, and then having you matching line by line. Pseudocode actually widely used by many professional, textbook, and workplace. And why is that? So in real life, you cannot assume every software designer, programmers, engineer know every language, no C++. You cannot assume all these people, they all know C++. So when I write my code, I just write in C++ and give out to these people so they can understand and read it. But actually, some of them only know Java, some of them only know Python, some of them only know C. So that's why it's not good to assume that everyone knows C++. So that's why pseudocode is the best way to help you gather all these engineers together and help them to read your code easily or read your logic or algorithms. So by sending this is like plain English, and this kind of like universal. So those programmers, they can read this thing easily. They don't have to know like C++ before in order to read this line. They don't have to know C# before to read this line. So that's why most of the textbook about algorithms using pseudocode, because in order to like have more like broad audience together. And also in workplace, software engineer also using this too, because they cannot assume like, oh, this guy knows C++. Just make C++ pseudocode. So they can figure out on their own, but actually not. Some of them don't know. So yeah, it's very safe and clean to do pseudocode. Okay. So now, since we already have the flowchart, and we also have the pseudocode, you see those two matching each other, because this thing is just like a pseudocode representation of the flowchart above. But now we want something real, like Python, like the real code, programming language. So for this example, I will pick Python because it's very simple. So now let's see how Python gonna look like. So this is the Python representation of the flowchart and the pseudocode. So you can see this line matching each other. If you're above 90%, just kind of like if grade greater than or equal to 90%, I give you an A. So I just print an A out. Next, keep going on until F, which means else right here. Okay, and also the Python programming code, you can also convert it to the flowchart. And from the flowchart, you can convert to here. And from here, you can convert to here. Or another way around. So actually, those three images right here are like interrelated. They can be interchangeable. So you can pick any method that you prefer. So I can give you some example. You can choose this thing as a new programmer, a beginner, or like you kind of like new to programming. You can pick flowchart representation because it's like highly organized and it have like a better visualization. You can see I have a chart, I have a flow, an arrow, and yes and no. Very organized, very useful for beginner. And let's say you are an algorithms designer, and you cannot assume like everyone know one language. So that's why the pseudocode is very useful for you to make, because after you writing your algorithm code like this, you share it to everyone. It's just like making a cake. You write a recipe of the cake in English, and then you send to everyone who know English, or even the Italian. They can use Google Translate to translate your English like recipe into your own language. So pseudocode is something like universal for everyone, regardless of their language or background. And as another scenario, let's say your team is like have 90% or 99% like Python user, like they know Python. So you can write the real code in Python. That's fine, because everyone know Python. So you can share this to everyone who know Python. So now back to algorithms. So why algorithms so important? So algorithms is actually the core in the brain that guide the machine how to work. Without an algorithm, the machine doesn't know what to do. So let's say a grading system. Let's say you build a robot that help you to grade your student assignment. And you know, the robot's not like us. Like they not like going to school. They don't know GPA. They don't know the grading system. They don't know tardy. They don't know detention. They don't know any of that because they just build from scratch. So that's why you have to feed it with your algorithms. So our algorithms can be represented like a flowchart like this. We feed it to the machine. Like tell the machine, hey, enter in grade. If this filter, give an A. If this filter, give a B. If this filter, give a C. Things like that. Okay. so the machine can know what to do. So algorithms kind of like the brain of the machine. And sometimes algorithm can be slow and fast because in real life, just like cooking recipe, some people they're making some like Thai food, but like require you like a long hours to finish it, and also can require a lot of like money to buy ingredient. So that's why also similar to algorithms, this can be also slow and fast and cost more or big memories, depend on the application. Because of the speed and the cost of the algorithms, computer scientists, engineer, designer, they invest the time to study algorithm analysis and the optimization in order to improve the efficiency of algorithms. And what the algorithm analysis gonna analyze? They gonna analyze the time and the speed. And for example, the time, they wanna analyze how fast or how slow is it of the algorithms running on a machine. And also they're gonna analyze how much space the machine gonna use just to run your algorithms. And after analyze, they learn how to optimize, how to make the time faster, how to make the space smaller. So that's why analyze and optimization go together. So now, what's the time and space complexity? So time complexity will determine how fast and slow the algorithm will perform on the machine. Just like how fast the machine gonna work when it's run like a certain like instruction that you feed it to it. And space complexity will determine how much the area, the hardware, the memory that your algorithm we're gonna consume on a machine. And there's a trade-off between time and space, because like sometimes when you try to optimize the time complexity, the space can be right. So let's say you create a dictionary software. Before that, you have to import to your dictionary machine like a lot of like vocabularies that already exist. After you importing everything, the searching time gonna be faster because the machine have a big data set of vocabulary, so it can search faster. But the trade-off is that like you need a huge memory to store all that, like maybe let's say 3,000 vocabularies. Otherwise, if the machine doesn't have like a predefined like set of vocabulary, the searching time gonna be slow because like it can look at like different source, different web page, or any different thing that you try to find the vocabulary that you asking with. And because of time and space complexity, is also like what a major problem that engineers are concerned and try to work to optimize time and space in real life. Okay, so now let's go back to another topic called software versus hardware performance, and how this thing relate to the time and complexity and also algorithms. So hardware perform like faster than software in general. And why does that happen? So let's have some example. Let's say I have a logic circuit right here. If you create hardware, you just input a signal, let's say A and B, and then it just jump out right away. You see, you provide a 1 0 here, it's gonna have another signal right here. So this is an implementation of have adder, just like an adder. So 1 0 gonna give you 1 here. This thing gonna be 0, and we're gonna assume that like all the hardware logic, all the logic circuit running with a constant time. So let's say a C. Why saying that? Because like relative to software, the hardware like logic circuit run like pretty fast, like relative to software. But in real life, if you compare like one logic with another logic, let's say you add another AND gate right here. So to see this one taking longer path to reaching here compared to previous one. So this logic compared to another logic can be like slower, but if they all compare relative to the software, then it's kind of like constant time. So let's assume it's C. So therefore, the total execution time of the hardware logic gonna be C, which is I put right here. So now let's come back to some software example. Let's say you're a programmer, a software engineer. You're writing a C++ code. Right. So for note, this code right here is just like example. It doesn't mean anything. I just show you an example like how C++ code gonna be compiled on the machine, and then how it's gonna guide the logic hardware to work. So it's just like nonsense code. So let's say you have C++ code. After you compile it on random machine, it's gonna convert it to assembly code. And assembly code gonna be converted to machine code, which is binary 0, 1, because machine only understand 1 and 0. It doesn't understand like English like this, complicated English word like this. And after it's have like 1 and 0 and 1 and 0, and this thing gonna be stored in the memory, and the processor gonna fetching these instructions from the memory and then tell the hardware or the logic circuit what to do. And let's assume the runtime of the C code that converts to assembly gonna be X, and the runtime, let me write it. Runtime assembly code to machine code gonna be Y, and the time for the machine code to tell the hardware what to do is Z. And the runtime hardware cell, we reassume it's just C right here. Therefore, the total execution time is gonna be X plus Y plus Z plus C. And you can see this thing is way bigger than the hardware implementation alone with just C, right? So this thing is bigger than C because software costs more time and also memory than hardware. That's why computer scientists, they have to make sure the time and space complexity had to be optimized. And so that's why we go back to here. When you a software designer, you have to take into consideration the time and space complexity. And because of that, you have to study how to analyze a better algorithms and also how to optimize it. And after you do that, after you analyze the algorithm, optimize it, your code will be faster. And after it's faster, your machine gonna follow it and working beautifully. So you see, at the beginning, we're gonna flow this way, but in the end, we can also flow another way if everything like time and space gonna work well.